Yes. So I have a hard task. Good afternoon to everyone. A hard task to compete with a movie. I'll do my best. And first of all, I would like to express my gratitude to the organizers of this excellent meeting. Very enjoyable, interesting talks, and I'm looking forward to the coming 2 days of 1.5 day of the meeting. I'm going to talk, actually I couldn't decide whether I'm going to talk about efficient market, inefficient market, about the hypothesis or the market, so I put all of these together, and you'll see why. As far as I can see the screen, I'll try from various directions. I hope this doesn't affect you hearing me. You probably heard about this person, Professor Thaler, who won just a few weeks ago. He got a Nobel Prize in economy, right? He has very good reasons to be happy, because this is associated with 9 million Swedish crowns, and that is 1.1 million US dollars. And he quickly proclaimed that he's going to, in an interview, oops, sorry. My movie is not going to work as smooth as it seemed. So he's going to try to spend it as irrationally as possible. Of course, what is the rationality of the market? We all know this is the market which doesn't crash. All the efforts done by economists who are quite successful in winning Nobel Prizes for killing the Homo economicus, who is the rational market agent. Right. Well, it's all about human decision-making, the decision-making which is made by mind of the agents, right, of the irrational agents taking part in the in the economic competition. Now, what are the reasons which are being mentioned for this particular Nobel Prize? That is the endowment effect, which I believe you may know. The loss aversion, that is the endowment effect, is essentially associated with what you have is you are more attributed to what you already possess than what you don't possess. The loss aversion, this roughly translates to it's much more painful to lose $1 than to gain $1, or 1 million for that matter. And the third one is the status quo bias. So by all means, we are trying to maintain our status quo. All of these actually are different expressions of one and the same underlying core. So this is the so-called cognitive bias. Well, obviously, to have cognition, you need to have a mind of some sort. You need to have cognition which expresses this bias, but then you see psychologists list many, many more of the possible cognitive biases which probably play a role in the mind's decision-making of the minds of the agents on the market. Now, that actually is good news for many of you who are in the field of economics, maybe not econophysics, but you see, taking 3 of them wins you a Nobel Prize. Now, here there's about 200. So you can make, maybe next time you need to choose 5 actually. Why is that? Because right? Because the so-called prospect theory, which is roughly equivalent to all the three which I listed, won a Nobel Prize to this gentleman, but that was a little bit earlier. So roughly in maybe 15 years' time, someone probably will win a Nobel Prize for 5 of these. I hope it will be one of you. Now, prospect theory essentially establishes this, what is equivalent to the relative pain, the amount of pain and the gain, pain for losing this $1 and relative less satisfaction of winning that $1. Now, all having the little bit of a joke at the Nobel Prize in economics, the problem is that, of course, we don't have a good understanding of financial crashes, and this is where everybody tries to make money on, including econophysicists, of course, which we some of us represent, Obviously, economists are much better in this, at least some of them, those who win. Now, looking back at econophysics literature, you see in 1999, I'm not sure you can read the list of authors from the distance, but I can assure you that these 2 papers were substantially influential, and both essentially in 1991 and 2010, both of these papers essentially stated there is absolutely no theoretical reason to expect, suspect, or prove that crashes in the market are critical, not even speaking about log periodic oscillations, which many econophysicists, like, for example, Johansen et al., try to propose as leading warning signs to a crash. Now, so what is left? What can we do with this? Now, there's a beautiful machine which I particularly like, and what has the name of what's to do with criticality is the question. This is a thermodynamical machine, a steam engine, which essentially runs on phase transition, right? Because it runs on water which is turned into steam, and all being well, it can run pretty reliably. And it did. Now, how can you crash it? How can you crash such a robust system? This is an almost perfectly rational machine. This is one oscillator, and here's another oscillator. This little oscillator is actually a controller. It's linked by feedback, and it controls the opening of the valve, which delivers steam. So it's all a feedback system of 2 coupled oscillators. Now, the story goes that actually Watts, who designed it, crashed it, and crashed it in such a way that initially his machine worked very well, but then he decided that this controller worked very well, but he decided that he will improve it. So the next time he polished all the parts very well, but the machine stopped working. Now, you very well know that from an analysis of damped system, you have some critical damping which you go out of this region of the stability of the system, you will obtain a system which starts oscillating. So his controller started oscillating and ultimately crashed. So obviously, analysis of systems, stability of systems, of linear systems, and even nonlinear systems is a very well established field, which has to do a lot with the poles. This is partly reference to my nationality, and that's why it's all written in Polish. But you see, analysis of this gives us very exact reasons to refer to stability of the system, to determine the stability of the system. Now, we don't actually need the Watts machine to show what is going on in such a system, and Haken proposed this kind of a very simple experiment, which I encourage you to do. I demonstrate this very often because it's something that you can do at home. This is science at home, or even at the conference room. So that is, you essentially take two fingers and you move to left and right, and faster and faster and faster and faster. Now then you, at some point of increase in frequency, you will see that your hands start moving towards each other. And that is exactly when the two oscillators, which are coupled through your body, start coming to a point where the phase transition happens. And this is a phase, which is really a phase of the two oscillators, the difference in the phase. But what happens here is a very special point, that is the point of criticality, in which the amplitude of the movements of the fingers of your arms increases, like divergence in the critical phenomena. So this is a beautiful example, very simple, for which Haken, by the way, didn't get the Nobel Prize. He tried a bit harder, so that is, he suggested one oscillator, which is almost like prospector theory, except within third power here for the anharmonic damped oscillator, which exhibits exactly the same kind of folding bifurcation, which I'll show you, as these two coupled oscillators, and the whole zoo of phenomena which is associated with critical transition, continuous transition. And that is the critical slowing down on approach, soft mode, and hard oscillations, and as well as symmetry breaking, instability, and critical fluctuations, increase in critical fluctuations and correlations. So even with this one equation, you can obtain this kind of a topology, which is a very generic topology. So obviously, one equation does not describe mind. Neither does one equation of the prospect theory does exactly describe of the mind of an agent, right? This is the critical point which I'm referring to. The interesting thing is, of course, that critical phenomena, as they are investigated in thermodynamical context, have to do with the number of particles, which is very, very large. And I find it quite convincing to look at the van der Waals equations using the equal area construction and deriving the critical point and the whole two branches of the phase transition. Then, then turning it 90 degrees, and what you obtain is the same topology of the critical dynamics. So in other words, it doesn't matter whether you have one agent which is anharmonic. It doesn't matter whether you have two coupled oscillators, or whether you have an infinite number of gas particles. They all show the same phenomena, which is encoded in this kind of a bifurcation. This is quite spectacular. This means that we can reduce the number of degrees of freedom and explain phenomena by means of a very, very simple model. This is, of course, extensively done by physicists. Not only by physicists. This is a paper which appeared in Nature explaining, at least trying to explain, a number of phenomena in ecology and in biology with critical warnings. But you see the same kind of fold bifurcation here, right? This is kind of a review paper which concentrated on the phenomenon on competing species. And in this example, the species, one of the examples, the species were the trees and the budworms, which were eating them. So the trees grow a little bit slower. The budworms eat them quite fast because they are hungry. So the result of this is that when you analyze the system using an equation, which I'll show you in the next slide, you get the same, exactly the same fold bifurcation with a catastrophe in between. So this is the unstable regime. Now the equation is here. And of course, on approach to this critical point, you do get skewness and flickering and all kinds of, and slowing down, all kinds of phenomena which we see in gases and other model phenomena which are analyzed in the context of critical transitions. And the thing is that this particular population dynamics has been described a long, long time ago. So another hint for you, you can win not, if you fail to win the Nobel Prize, you can at least write a Nature paper using someone else's equation from, say, 20 years ago, which everybody forgot. But then you come up and write a paper in 2000 and maybe 20. That is not a proof of anything wrong, by the way. That means that this science works, and somebody simply has to bring it back, remind it. Obviously, worms in the ecological setting are irrational agents from the point of view of economy because they eat everything which they can see. So now let me slowly go to people. Apparently people are irrational too. And the proof of the pudding, right, is that when I dug up some old slides, and that is 2006, which seemed like a century ago to me. But when we published this paper, the whole zoo of journalists came. I never got so many letters, emails from homegrown investors, because physicists can predict stock market crashes. That's good news, right? How did we manage to achieve this kind of fame? Well, actually, it was quite simple, because we took a model of PDF, which has been proposed by Castaigne in the context of fully developed turbulence. Now, this model is very simple. It's only a multiplication of essentially two processes. One is normal, the other is log normal. So one of them has a parameter which controls the width of the tail. So how heavy is the tail of this distribution? And this distribution can be described by this Castaigne's equation, starting from, for lambda going to 0 from Gaussian distribution, which here in the logarithmic coordinates is shown as an inverted parabola, to essentially almost a 10th distribution for heavy tails. That was proved to be quite practical, this Costain's equation, obviously not only in turbulence. This I took from the heart rate analysis, but it's not only for the heart rate, because this is truncated Levy flight. So you see here the resolution of analysis, and that is simply the window in which we take this time series. We determine the distribution at this resolution. So starting from very fine resolution, we go to very large resolutions. Now, for a system like this one, for example, right, if we take very fine resolution, we see these large tails, but going to very, very coarse resolution, large scales, we see transition to a Gaussian. Now, this is shown here in showing the dependence of this lambda parameter, which describes the tails strength. Going to 0 to the Gaussian process, you see different rates of going to the Gaussian. For truncated Levy flight, this is a model which was used by many to describe financial time series. But you see that although it starts at very, very high for fine scales, very, very long tails, which, by the way, will lead to multifractality, but it goes down as essentially a power law here. You don't see this as a power law because this is logarithmic scale. So the only power law that we actually see here is the cascading model. So this is a logarithmic dependence, right? So this is a logarithmic dependence and cascade model. So cascades as in multifractals. Cascade, this is important. Cascades which are described by a kernel which is invariant across resolutions. Like fractals. Fractals have a certain generating pattern, generating rule. Cascades, multifractal cascades, have a certain generating kernel, and this cascading model has this kind of a logarithmic decay. Every kind of a non-correlated process will decay in a fashion which is described essentially by Berry-Essen theorem, which is faster than that, not slower. It cannot go down slower. This is simply the consequence of the central limit theorem, which is expressed here. So there is one process here, and that is coincidentally human heart rate, which does not seem to go down to 0, which doesn't seem to reach this level of Gaussianity, even at very, very high, like 3 orders of magnitude. While financial model, truncated Levy flight model for financial time series would reach this very quickly. Cascade model for multifractals, it would reach it in the end, slower, logarithmic rate. Of course, autoregressive model, which is shown, I believe, somewhere here, it's just all everywhere described simple autoregressive model. It simply is a Gaussian model, uncorrelated Gaussian. So it doesn't change with resolution. Now, what did it bring with this kind of analysis for the financial time series? Well, it brought a very nice picture for this is essentially not taking into account any crash of named crash. And that showed us beautiful analogy with turbulence. So this is the lambda square, which is not exactly logarithmically decaying. It has a clearly defined region of viscous dissipation, but it also has this range which I think some of you would argue this is linear, so it is a logarithmic decay. But then this is log-log plot. So actually, there's almost no way of deciding whether this is a cascading process. or not. For the financial, for the Standard and Poor index prior to Black Monday, which is kind of a reference crash. You see, this is not really unique to finance, because the same kind of discrepancy between logarithmic, semi-logarithmic scale and double logarithmic scale has been shown for turbulence. So this means that the process is actually a little bit more complex. In the area of Black Monday, the story was completely different. And this different story is shown here in red, right? So for the area which is centered here around the Black Monday crash, we didn't see the near logarithmic decay. We saw essentially data collapse, PDF collapse. And that is a very good indication, critical, essentially critical point. This is not the only indication. We have seen several other indications. So this is work which is more recent. This is 2016 on different time series where we have analyzed not only, actually we didn't analyze PDF, but we analyzed a lot of other precursors of the crashes, showing that they can actually generate, that the crash itself can be very well described by the fold bifurcation, as well as provides all kinds of indicators like skewness and slowing down and flickering. Now, in the very point of the crash, this is a picture which describes in more detail the kernel, the kernel of the correlations. And you see that this is not scale invariant. In green, it describes the kernel of two-point correlations for the region outside the Black Monday, and in red for different time resolutions, temporal resolutions. This red describes this kernel for the region which is isolated from the around the 80s Black Monday. So you see, first of all, that this is not scale invariant, which again proves that this is not a multifractal cascade. It is close, but not multifractal cascade. The correlations are much stronger in the critical regime of the Black Monday. And you also see some residual oscillations here. I was quite surprised to see this. I saw it after publication has been done when I was thinking about log periodicity in the sense of Johansen and others who tried to fit it to the data. Well, this is not fitting to the data. This is statistical oscillations in the two-point correlations which happen here. And this is, of course, a logarithmic scale. So these are statistically log periodic oscillations, but not in the sense you cannot obtain them by simply fitting to the data. This kind of kernel has been actually described much earlier in 1998 for the time period after the crash from 91 to 96 by Arneado et al. There was no mention there, as far as I remember, of lack of invariance of this kernel with regard to scale, but very beautiful description of so-called information cascade spreading for up to about 3 months. So, yeah, these are just traces of some correlations. Now, what about prediction, risk and prediction in the context of this work? Because we have PDF, you see, we have exact PDF which we can fit. We have details. So we can quantify the risk. And by means of quantifying this risk, this is the tail which here exceeds the top level. You see, this is essentially years before. And slow climbing of this, to me, if I were analyzing now, this is beautiful work of post-diction. But the probability which we calculated of the crash, which is 10 sigma, before reaching the actual 2 months period around Black Monday, was already 100 times greater. And 10 sigma is a lot. This predictor, so the non-Gaussianity of the stock market is actually a very strong, I would call it a replacement for the volatility, which is commonly used for this purpose. Now, what about the agent behavior? These are other characteristics which we calculated. That is 1/f spectrum in the using DFA, using the power spectral analysis. What is 1/f? Obviously, 1/f is a pink noise which happens in the context of criticality, right? So financial system is obviously a biological system as well, because if we agree that it's irrational, so this is a system with minds of some sort. This is the Hurst exponent, and one important conclusion from the work by Białek in the context of biological system poised at criticality is the dependence, the characteristic of the critical state in terms of entropy, which is a linear function of energy. It's again a description of critical point for any kind of a system, regardless of the number of degrees of freedom. These degrees of freedom get reduced on approach to criticality. This, I dug out a very old work, which even I could do myself by means of wavelets very many years ago. And that showed, again, for the Standard & Poor index around the crash, a very simple analysis which you can see here by using wavelets. So this is the area prior to the Black Monday, this is post, and these are two singularities which lead to the crash. Now, if you look at these two singularities, they behave essentially very different in terms of their scaling from the rest of the prior and posterior behavior. What you see here is essentially almost no slope, and that means that this is equivalent to pink noise. This is pink bifurcation. Two bifurcations, because one wing, when you convolve a Gaussian Mexican hat, sorry, second derivative of the Gaussian, with Black Monday, you obtain returns, you obtain two branches of the maxima tree of wavelet transformer. One describes what happened before, and the other describes what happened after. And the rest of the time series is essentially characterized by a multifractal spectrum of singularities, which are all distributed around this random walk-centered multifractal. This is just very old historical stuff. Now, what I want to mention here now is that this whole area of multifractal behavior centered at 0.5 is essentially when we think about random walk, right? Not even random multifractal. This is an area with maximum entropy. Now, we just discussed this, that in the Black Monday regime, we have entropy minimization. We have and that has been actually done by many people, also in the context of Ising spin and very generic formalism. What does it mean in the terms of the agent behavior? Now, this is not a published work, but I would just say that so much that essentially for these two different regimes, because of the asymmetry of entropy minimization and entropy maximization, we essentially can classify this regime as the regime of agents who facilitate risk-taking, and that corresponds with entropy maximization and random walk-centered multifractal, while in the regime of criticality, we get a flip. Essentially, this is a regime of risk aversion, which is done purely using topological optimization. And this, hopefully, will put up in xArchives very, very soon. So much for this. Obviously, we need intelligence to crash the market, right? And here I'll invoke a little bit of a philosophical thought on the human mind. A man, this is Turing, by the way, a man equipped with a paper, pencil, and rubber, and subject to a strict discipline, which is very important to me, is in effect a universal machine, right? So you know the famous Turing test. You know that essentially this involves talking through some channel, communication channel to a machine, trying to find out whether it's a human with a brain or it's a machine. Now, with the progress we are currently making on AI and big data, it probably will be like maybe in 20 years and not 200 almost, that this Turing test will be the next Turing test, and that is yesterday I made the Turing test. The interesting result. I failed. The machine realized immediately that it was a dumb human. So now I'm closing slowly. Slowly I'm coming to the end of this philosophical debate. I'm not sure whether you are aware of the previous fever in AI. And AI has managed to die already at least 2 times. Now this is the 3rd time it's alive. That was the big China experiment. Now if you equip all the people in China with walkie-talkie, that was at that time. Now everybody has a mobile phone. And if they all start talking to each other, will this be a conscious entity? Will this be a brain with a mind? Now, obviously, some people said yes, some people said no. And nobody has done it yet because China has a strict policy on the internet. So if they lift it, maybe we'll be able to test this hypothesis. There's another Chinese, this is my last Chinese experiment, and that is the Chinese room. And again, the story is that you need to put someone in the room, and you give this person essentially question written in Chinese and through a hole, and then you get the answer, also written in Chinese. Now, I assume you can read Chinese. If you don't, then try it in your own language. The thing is that the question that if you get the right answer is you don't know whether somebody who is inside, who answered your question, has mind or doesn't have. Now, essentially, what inside the box is just a man with a number of dictionaries and books, all the human knowledge he can find, so, or maybe the internet connection. And these were the toy examples of the previous AI revolution. but essentially there is no cognitive bias here. This is just a machine. This is just a set of rules which obviously are put into the books by interacting machines. And to me, I'm closing here, essentially mind and consciousness and irrational agents are all a product of interactions and can be simplified by reduction, data reduction, and simpler approaches which physical economists are trying to propose and failing so far to get a Nobel Prize for this. Economists are much better in this. Thank you. Okay.
So we now have a couple of questions. Questions?
Is there an advantage to try to fit the tails with this time varying parameter for low number distributions versus, say, fitting this distribution with a student's T distribution and then plotting the exponents as a function of T?
You're asking whether there's an advantage in fitting this particular model? Well, the advantage, there's no advantage regarding any kind of a parametric model that you're fitting. No, it's just the simplicity of the model and the explicit means of how well it fits, essentially, right, to the data. So I would say you can fit absolutely anything as long as you do it at multiple scales and as long as you can quantify the heaviness of the tail. So that, for the rest, you are free to fit whatever you like.
But I was wondering about, say, the precision or efficiency of the fitting parameter. That was my question. Is it more efficient, more precise with your way?
Yes. It was both elegant in the sense of fitting and of the mathematical approach, and efficient. Yes. We have proposed several methods of fitting this. It was done in the simplest way, but also in some more complicated, so like simplest, of course, minimization of the root mean square distance. But there are other ways possible, fitting through moments and others. This is all published a long time ago. Okay, in between the questions, I'll just advertise a topic which you're welcome to submit to, and I'll close with this.
No more questions. Let's thank the speaker.